Welcome to the first section of calculus, and we will start first by talking about limits. We're going to take a numerical and graphical approach in this section. And some of these sections I'm going to present in a slightly different way, where we're just going to start with a problem and kind of work out some things, and we're going to start with a problem. And in the beginning, we're just going to talk real general, not math notation, just kind of see what's going on with the problem, kind of like an activity. Then from there, we'll add some notes in the margins, and that will be more math notation. And then after we've done the problem, we'll do the formal mathematical definition. It's a little bit reverse of what you might see in a traditional math video. Let's go ahead and get started with this problem. Steve Nash has the second highest lifetime free throw percent, which is 90.43%. And you decide you're going to study his free throws in greater detail to improve your own shot. But unfortunately, as you're recording, the video freezes. What we want to do is try to accurately guess the height of the ball after 5 seconds. So we have a couple screenshots. The first is at 0.2 seconds. The next screenshot is where it blacks out. And then we have a screenshot from 7 seconds. And the ball is here in the 0.2 second screenshot, and it's up here in the 0.7 screenshot. What we need to do now is answer these first 3 questions, and then we'll stop right there. On question 2, you'll see that you will receive several data points from your ball's path. I'm going to put those up here in just a moment. And the time will be given in seconds, and the height will be given in feet. Part 2A is asking us to record the data from before the video froze. And the time frame that we're going to use on that is given in this question up here. It says, how accurately can you guess the height of the ball after 5 seconds? So before the frame froze is at 0.5 seconds, and then after we'll do the 0.5. So we'll do before 0.5 and after 0.5. And what we want to do is start with the smallest value here and work all the way up to the one closest to 0.5 before the video froze. But here we want to start with the largest time and work our way back to the smallest time after the video froze. So I'm going to go ahead and put these cards with the times up on the screen. And this is a great place to pause the video and fill in questions 1 through 3 with this data here helping you with question 2A and 2B. Okay, now I hope that you have taken the time to answer the questions on this first page. From here, I'm going to go ahead and add some notes to this page. And what I suggest for students to do is to change your pen color and maybe keep that consistent throughout all of these calculus videos. That way, when you're referring back to them, whatever color you have chosen stands out. A good choice for a color is red because that just naturally pops, but the choice is yours. All right, so let's go ahead and look at this problem. We want to find the height of the ball right before the video froze and right after the video froze. And to approach this problem, I gave you some data of the time and the height of the ball at that time. So here is what those 2 tables look like. We're going to go ahead now, instead of just looking at it as data, we're going to start thinking of it in terms of a function. Well, this is going to be our variable time, and then this will be height as a function of time. Now, something very interesting is happening here. If you notice, as we keep moving this way, we see that the height is getting closer and closer to 15. The way that I'm going to write that mathematically is I am going to say the limit, written as LIM, as t, the time, approaches 0.5. As you see, all these times are getting closer and closer to 0.5. So that's what that is. And I'm going to put a little subtraction looking sign right there. What that means is I'm coming from the left-hand side. So the limit as t approaches 0.5, we'll say from the left, and then here we have of the function h of t, that is going to equal 15. So all of that data can be summarized in this mathematical notation. In the next video, I will give you formal definitions, but we're just starting to see what this problem looks like. Now let's look at the part after 0.5. That is going to be the limit as the variable t approaches 0.5, and we're coming in the opposite direction as we're getting closer and closer to 0.5, but we're coming from the right-hand side, or we're coming from the larger numbers of our function. This is also going to equal 15. You see, we're getting closer and closer to 15 as we go from far away from the right to very close to 0.5. Now, since the limit from the left and the limit from the right are the same, we can write this as the limit as t approaches 0.5 of our function is going to equal 15. They're in agreement. And you may have predicted for part C that we feel pretty confident that the height will be 15. Now here we have the height of Steve Nash's free throw is given by the following function. Now I'm going to go ahead and put this in Desmos. It's a lot easier to present a graph on Desmos when I'm making these videos if I put the graph in Desmos versus in your graphing calculator, but you could do the exact same thing in your graphing calculator. I do want to go ahead and put in some bounds. Okay, so I put the domain in there just according to what the problem said. You'll see we have a nice curve, and you can go ahead and copy that. And you'll see this is what it looks like if we do it in Desmos. What we're trying to find out is the height at 0.5. So on that table, what we did is we saw everything coming from the left and then everything coming from the right. We saw that from the left, it was 0.5, and from the right, our output would be 15 feet. Now, on this function, we can say that h of 0.5 is equal to 15. This is the actual height. Up here, we were predicting that the height was 15, but then we're given a function and we can find the actual height. Why do we need to predict the height using limits if you could just give me the function and I can tell you what the actual height is? And that is a great question, and that will be answered in the next video.